Hello, so in this video I'm going to be explaining how to determine the density of a log that is floating in water, assuming the log is a perfect cylinder. So the first thing we would have is, I'll draw a picture of the log. So here's our log, which is assumed to be a perfect cylinder. This is the radius of the log R. This is the length of the R. We'll call that capital L. And then up here, this little portion right here is the height of the log that is above the water. So we could assume that the water level goes across right about here. So certain things to note about this picture is that we could assume that the velocity of the log is 0, which means the acceleration of the log is 0, which means the net force on the log is also 0. So what that means is that we will have a buoyant force, which is equal to the displacement of the liquid, and that will be equal to the mass of the water times the acceleration due to gravity, g, is equal to the mass of the log also times the acceleration due to gravity. So then what we can do with this is we have g on both sides, so we can cancel them out to get the mass of the water equals the mass of the log. So from here, what we can do is further explain what the mass of water, mass of log equal, and what mass of water equals is rho of water, which we are using the variable rho, which means density. So this is density of water, which is about 1,000 kilograms per meter cubed. So we have rho of water times this cross-sectional area of the log that is under the water equals the density of the log, which is what we are after, times pi squared. That does not look like a pi. So the only thing we know that the density of water is 1,000 kilograms per meter cubed, and we know pi squared is the area of circle. So our two unknowns are the density of log, which is what we are after, and then this area of the cross-sectional surface. Well, this area of the cross-sectional surface also we could say equals the area of the full circle, pi squared, minus this little top portion. Well, we'll need to know what the area of this little top portion is. So in order to find that, we can say that the area of this little portion equals a circular sector minus the triangle that is made. So what this looks, first we'll have to get the area of this circular sector, then this triangle to get this, and once we have this, we can subtract it from pi squared, to finally get our value for this cross-sectional area that we want. So I'll draw a picture to illustrate exactly what we are talking about. So here is the center of a circle. This is a radius r, and then, that is not a good line. Here is another radius r. Still not a good line. Well, you can tell that this shape right here is the one that looks like an ice cream cone, just very flattened out. So then if we were to draw a line here for the water level, we have the height h. This is really not a straight line. And then this middle portion is r minus h. Because originally from the center of circle to up here would be r, but instead we have crossed off and put h, so it's r minus h. And then another important thing is, for later, is we have some angle here that we will call theta. So now that we have all of that information, we can go ahead and write down the area for the cone. So we'll get 2 theta over 2 pi times r squared. So if you notice here, we have, and this 2 theta came from the 2 thetas that were split in the circle, the triangle. So here you notice we have 2 over 2, which equals 1, and we have pi multiplied by pi in the denominator, which equals 1. So this will equal theta r squared, because this cancels, this cancels, this cancels, this cancels. Well, theta, we don't know what theta is, but we can figure it out using sines, cosines, and tangents and all that stuff. So we're going to solve for theta, and we are going to have theta equals cosine inverse of r minus h over r. And this just came about because cosine of theta is the adjacent, which was r minus h, the middle portion, divided by the hypotenuse r. So to get theta by itself, we take the cosine inverse of both sides. So now what we have is r squared times cosine inverse of r minus h over r equals the area of this ice cream cone. So now what's left to do is to find the area of this triangular portion. So we know that the area of a triangle is 1/2 base times height. So if we were just to pick some random variable x and plug in for the base, we would have 1/2 x minus h. But what we want to find x. So what we're going to do is use the Pythagorean theorem, a squared plus b squared equals c squared, to solve for the base. So like this x would be up here and all that stuff. So what we are going to do is we're going to use the Pythagorean theorem. So we will have x squared plus r minus h squared equals r squared. So we want x by itself. So we're going to subtract r minus h and take the square root of everything. So what we will end up getting is x equals radical r squared minus r minus h squared. And what will happen in here is r minus h squared is equal to r squared minus 2rh plus h squared. So the 2r squares, since it's subtracted, will cancel out and we'll distribute the negative. So what we'll end up having is a radical sign. 2rh minus h squared. Again, because the negative sign would distribute throughout, turning everything the opposite side. So now we have an expression for what x equals. Well, we can go ahead and plug that in for the triangle. So what we're going to end up having is 1/2 we're going to have 1/2, trying to remember what was, radical 2rh minus h squared, and then r minus h. Now, if you remember, we had two triangles for the giant triangular portion, and this is for only one. So what we're going to do is multiply all of this by 2. And let's say this equals a triangle. Well, now the 2 and 1/2 cancel out. So we're only going to have So now we're only going to have radical 2rh minus h squared and r minus h. So, since we know what the ice cream cone area is and what this triangle area is, well, now we can subtract them to get the area of the shape that was kind of like this half circle. So let's go ahead and do that. So we'll have this r squared cosine inverse of r minus h over r. I should have wrote this a little over to the left because I think I'm going to run out of room. Minus, and we're going to put parentheses here so we don't leave anything out. Radical 2rh minus h squared r minus h. And this equals this little circle-ish area. Kind of gets confusing with all the parentheses, but we put an outer parentheses to make sure this negative sign contributes to all of that. So now we know the area for this tiny circle. Well, now we can subtract all of this from pi r squared to get the area of the shape that's almost like a smiley face or mouth, whatever you want to call it. So we can go ahead and do pi r squared. All right, now this is going to be a lot of parentheses and writing. Essentially, I'm putting all of this in this minus parentheses. All right, so now this is the equation for the area of this little portion right here. As you can tell, there's a lot of R's and H's, and it looks very complicated. But now we are almost done, because I'll erase this. Because if you remember, what we want is the density of the log. We know the density of water is 1,000 kilograms per meter cubed. And on the left side of the equation, we had density of water times this equals the density of the log times pi r squared, because the lengths cancel out. So actually, I'm not sure if here, I'll write it out because it's kind of hard to visualize. So we had density of water times this length equals density of log as a horrible row times r squared times L. So we had this, the lengths cancel out. We know what this is. We know what this is. We now have this. So now we just need to solve for density of the log. So now, as the grand finale, we will have the density of the log equals 1,000 times all of this I'll try and fit it all on one line. And we have all of this divided by pi r squared. So then this is the equation for the density of the log, in case you've ever seen a perfectly cylindrical log floating in water. This is how you would find its density. And I'll go ahead and repeat what this all is right here again, because I'd write small because it's a lot. So we have 1,000 times pi r squared minus r squared cosine inverse of r minus h over h. And we have minus the square root of 2rh minus h squared times r minus h. And down here we have divided by pi r squared.